Now that we're familiar with how to construct numerical vectors, we can get back to making an R script to do a sensitivity analysis. So I have our sensitivity analysis pipeline here, and I can go into the input to remind us of the motivation for this analysis. So we're thinking about exponential decay in the context of first order kinetics, and we've worked through this derivation. Now we want to implement some code that'll let us look at the shape of this mathematical function that was the outcome of those calculations, or those derivations, I should say. And ultimately, to do that, we need to construct some number of values for t at which we want to calculate concentrations C, such that we can look at how concentration changes over time as predicted by this model of first order kinetics. With that motivation in mind, let's get back to an R session to start building this script. I'm going to close PowerPoint, go back to the root of my pipeline, go to my protocol directory. Here's the RStudio project file that we created. And this is what I'm going to use to open up my RStudio session. As expected, my working directory should be that protocol directory. So I can see that I'm in the protocol directory here in my Files tab. And just to be sure, I can do a get working directory function call. And indeed, I'm in that protocol directory. And the next thing I need to do is then create a script. Now we're to the point where we're writing some code that we want to keep. We don't want to have to just keep typing it into the console every time. So there's a couple ways to start a script. There's this little icon at the top that shows a blank piece of paper with a plus sign on it. I can click on the arrow next to that and I can start a new script from here, or I can do File, New File, Script. Now a script is really just a text file, so I could also do this by starting a text file and just put a .r extension on it to designate an R script. But this is RStudio. It knows how to deal with R, and it has some specific things for creating R, particular types of files related to R. So I'm going to create an R script that will bring up a new tab in the text editor in RStudio. And initially it's going to be called untitled because I haven't done anything to save this file yet. So if I want to put a name here that means something, I need to save this file somewhere. So I'm going to click on the save button, and either this save button or this save button will do the same thing. And because I haven't saved it as a name yet, when I click the save button, it's going to ask me, well, what do you want to call this thing and where do you want to put it? Now in this case, this is going to be code, which is part of the protocol. So I indeed do want to put it in the protocol folder. And this is going to be the analysis part of my code. So for now, I'm going to call it analysis, and you can see it's already going to put a .r extension on there for me because I told it that I was creating an R script. So I can click save. Now you'll see I have an analysis.r in the protocol directory, and the name on the tab will change to the name of the file. So now if I click save again, it's not going to bring that dialog up again because it has a name of a file, and every time I click save, it's just going to overwrite the previous version with whatever I've added to the file. So this is the start of a script, and the first thing that I like to do with a script is do a little bit of debugging code that helps me make sure that there's not going to be any artifacts in my global environment that will somehow make my script looks like it's working when it isn't actually working. So whenever I start a script, I start with a function called rm_list equals ls. Now this is actually a combination of two function calls. I'm calling the function rm, and we talked about what rm does. It removes variables from the global environment, or it can remove them from any environment, but if you don't give it any arguments, further arguments, it'll remove them from the global environment. And a list is a way to give a list of files that you want to remove from the global environment. So the argument that I'm passing to rm is the list argument, and what I'm passing to the list argument is the results of a function call to ls. And if you remember, ls is how you get a list of all the variables in the global environment. If I call it no, there aren't any variables in the environment, so this will result in nothing being removed from the global environment. But the idea of this call is just to simply remove any variables that are currently in the global environment. And I've talked about this in previous videos. One of the really common problems I've seen with code is there's a variable in the global environment that has been defined manually, either through the console or through some other RStudio function. And then the script that you're writing will work because that variable is there, even though this script does not set the value of that variable. So this little bit of debugging code is really helpful for making sure that your program will stand on its own. It will be able to run because it will put everything in the global environment that it needs to finish its run. The next thing we need to learn is how to put comments in our code. If you're going to make reproducible data products, it's really important for somebody else to be able to read your code and understand what it's doing. In R, the way to add a comment is to start a line with the hashtag or the pound character. Anything beyond a pound character in a line of R code is going to be ignored by the R interpreter. So if we want to put a comment here describing what this rm list equals ls is doing, then we might add something here like avoid any bugs from artifacts in the global environment. This gives people an idea of why you're doing this in your code, and it's something written in an English narrative that lets them know why this code is here. Now we can start thinking about creating a numeric vector that represents the different times during some hypothetical reactor experiment at which we want to calculate the concentrations of a reactant. So I'm going to add some more code here, and I'm going to go ahead and put my comment in first to say create a vector of experiment, or let's say hypothetical experiment times at which to calculate concentrations. Now you're going to see me follow a code style where I keep my code fairly narrow. This line right here is at 80 characters, and it's a bit of a standard in terms of code to try to keep your code narrower than 80 characters. It has nothing to do with the function of the code. The code will work just fine if I go beyond that. However, you want your code to be readable. And if it's on a monitor that has a relatively narrow screen, you're not going to be able to see all your code without scrolling over. For example, if I put this out to the right, you can see a scroll bar appears, and if I have to see all of that material, I need to scroll over to see it. Well, that makes it hard to read your code. And code readability is really, really useful, not just for people trying to read your code, but yourself, your future self, to try to make sure you understand how your code works. So even when I'm writing comments, I'm careful to keep my code narrower, where I'll put the second part of the comment on a next line, add another pound character to continue the comment. And I even indent it a little bit to make my comment perhaps a little bit easier to read. We'll talk a lot about keeping code narrow and code style as we work further and further into this script. Now I need to assign a variable, and I've got to decide, well, what do I call this variable? Now I could use just a t. That's the mathematical variable that I'm using, but actually these days in most code styling guides, they encourage you to use words that mean something. We're not really that worried about how much space our program takes up in memory. There's so much memory that is really not that important. So it's better to use whole words to represent things rather than just individual letters. This is code, it's not mathematical notation. Mathematical notation is just the reverse. You do want to use single characters for math notation. But in code, let's just spell out the word time. And I also kind of use a convention, and this is not standardized or anything, that I like to use the plural case for time, saying that this is a vector of times. It's not just one time, it's a bunch of times. So I'm going to be assigning a vector here. I'm going to call this times. I'm going to put the assignment operator, and I'm going to use the seek function to create a vector of times. Now the seek function has several different arguments, but as before, we're going to use the from and the to argument. So for the from argument, I want to pass a value of 0 because I'm going to consider 0 the starting time of the experiment. And then 2, I have to decide what number to use. Well, here's where we have to think about the hypothetical experiment. Let's say we're talking about a reaction where we expect to see something like 10% of the reactant consumed per minute over the course of this experiment. Now, if that's the case, then we're going to expect to probably run down out of our reactant over the course of maybe about an hour if it's reducing by 10% every minute. So we want to see what goes on over an hour of this hypothetical experiment. And we have to think about units here to make sure we understand our numbers make sense. So if we're talking about 10% per minute, let's just stick with minutes as our unit and say we want to go over a course of an hour. That's going to be 60 minutes. And then we have to decide, well, at what density do we want to calculate these concentrations? So for this case, let's say, well, let's just say every half minute. And we can use the by argument to seek. And for the by argument, we can pass half a minute. Remember, our units are minutes now, so if we're incrementing by half a minute, we need to put an 0.5 in for our by. So now we should be creating a vector. Now there's several different ways to run code. There's a run button here, but be careful, that run means only run the code that's selected. So I could put a cursor on this line and hit run, and it's only going to run that one line of code. The source button is what you hit if you want to run all the code in a script. And there's a couple of different ways to run source. If you click this little arrow next to source, you can say source or source with echo. If you do just source, it's going to run the whole script without echoing it in the console. If you do source with echo, then it'll run the script and you'll see the lines of the script show up in the console as they're running, which is helpful with debugging if you want to see if there's a problem where it happens in your script. So for example, if I do source with echo, here's the rm list equals ls, it ran that, and here's the times equals seek. So it echoed this code to the console and ran it at the same time. And now indeed we have a times variable in our global environment. And we can look at that times variable by typing times in the console as we've done before. And you can see 0, 0.5, 1, all the way up to our maximum, which is 60. So I'm going to clear my console and I'm going to do a source again without echoing. In this case, it runs. You see the source function being called to run this code, but you don't see the individual lines of code echoing here. But it still ran. We still see the times. The times are still there. Same as before. Let me create another variable. I'm just going to say x is 2. And now you can see we have an x. And we're going to see how this rm list equals ls operates. Again, that's an artifact in my global environment. If I stuck that x equals 2 in there and I somehow used it in my code, that x equals 2, that x wouldn't be there the next time I started up r. And that would be a problem for my code because my code would suddenly break. It would say, what? There is no x the next time I ran it. So if I have this rm list equals ls, that'll make sure this is gone so that I don't accidentally write code that uses x. So if I run source again, you can see that the x disappears. Also, once you've run source, either with echo or without, it'll remember how you ran it the last time. And if you just click on the source button, it will do it the same way as you did it the previous time. So notice if I hit source now, it's not echoing. That's because the last time I ran it was without echo. And you can see that the x went away and the times is there. So that's it. That's the start of our script. And we're ready to move on and thinking further about this sensitivity analysis from here.